Hey everybody, this is Mr. Beckstrom, and today we're going to go over section 3.6. This is the derivatives as rates of change. So we'll see a pretty familiar formula here where first we're going to define the velocity as basically this is very similar to finding the slope of the secant line where we have some point A and then we have the delta t, which is the distance really between those independent variables. And this is how we can define the average velocity, and you just take the 2 points. There's a couple of different ways to do it, but this is one way to do it here. And then we can actually define instantaneous velocity as the delta t, or that distance between our independent variables, gets smaller and smaller as it approaches zero. The instantaneous velocity, which would be the slope of the tangent line at our point A, would be equal to that. And we can also define that as the derivative. So when we're talking about velocity and acceleration, we can use these new formulas that we have and really just calculate these. So velocity and speed are really the same thing, except velocity has a direction, whereas speed does not. So the sign of our velocity will tell us which direction we're going. So generally we'll assign one direction as positive and one as negative, and then that will tell us which direction we're going. But the speed really only cares about the absolute value of the velocity, so it's just looking at the magnitude. However, we can find the velocity or speed by taking the first derivative of some position function. And then if we take the second derivative of that position function, we can actually calculate the acceleration at some time t, where t is usually our time, which is actually defined in this case. So let's go ahead and take a look at an example and see how we would use this to solve for usually velocity, speed, or acceleration, but we can also be given those, which we're going to be due in later sections, where we're going to be given like the acceleration, and we're going to use antiderivatives. That's where we go the other direction, which is also called integration, to find the velocity and position function. But for now, let's take a look at an example from the exercises here. All right, so this is example 22 from, or exercise 22 from the book here for section 3.6, and it says a dropped stone on Mars. A stone is dropped off the edge of a 54-foot cliff on Mars, where the acceleration due to gravity is about 12 feet per second squared. The height in feet of the stone above the ground, t seconds after it is dropped, is given by this function here. Find the velocity of the stone and its speed when it hits the ground. Okay, so with a lot of these word problems, it's really helpful to go ahead and just draw yourself a little picture. So it says this cliff is 54 feet above the ground, and then let's say this is the ground here, and so this distance here is going to be 54 feet. 54 feet. And we are dropping the stone off right here. So this is falling downwards, which is generally going to be the negative, the velocity direction here. So the stone is dropped off this edge. Now notice they give us the acceleration due to gravity of about 12 feet per second squared. Now, initially, it may look like we need to use this value here, but it's really just kind of extraneous information. Why? Because here's our position function, and if you go ahead and take the derivative of this twice to get the acceleration, this is the acceleration that you'll get. In fact, this will really be negative, but because you get negative 12, and then you'll get negative 12, but remember, it's going in the negative direction. So if you have negative velocity going in the negative direction, then it's actually increasing here. it's getting faster and faster, which makes sense as the rock falls down. So, given all this information here, what we want to do, we can call this distance here 0, and this distance up here 54 at the top, which makes sense because our function adds 54. So it's really, remember, this is the position function. So when t is equal to 0, the position is going to be 54 up here, because that zeroes out and you just get the 54 there. So knowing that, we want to know what is the time going to be, the t time going to be, when it gets down to 0. So we can just really set up this equation here. Let me give myself a little bit more room. And we're going to say negative 6t squared plus 54. And we want to see what is the t, the time, when it gets down to 0. So that's the equation that we're going to solve to find the t when it gets down to the bottom here. So putting that in there, we're going to get negative 6t squared is equal to negative 54. And t squared is equal to 9. And t is equal to plus or minus 3. Now we have to think about it. We have a negative 3 and we have a positive 3. Why do we have both of those solutions? Well, because this is a quadratic here. And a quadratic is a parabola. It's a down opening parabola. And it's going to give us two different solutions. But one of them is going to be extraneous. And that's going to be the negative 3. Because we're not really interested in going back in time. We're interested in going from 0 forward in time. So really, we're just going to get a positive 3 here. So that tells us that it's going to take 3 seconds to get from 54 feet down to 0 feet. And using that, now we can find the velocity and the speed. So to find the velocity of the position function from above here, we're just going to take the derivative with respect to t there of the position function. So velocity of t is equal to the derivative of this. We'll just use the power rule and the constant rule there. So you're going to get negative 12t, and the 54 cancels out. Now here's the velocity, and we know how much time it takes to get down there. So let's see what the velocity is at 3 seconds. That means we're going to look at VF3, which is equal to negative 12 times 3, which is equal to negative 36. So that will be our velocity. And our speed is just the absolute value of our velocity. So the speed at 3 seconds is just going to equal to the absolute value of negative 36, which is equal to 36. And I believe this is feet per second. So that would be my final answer, feet per second and feet per second. All right, let's take a look at another example here. All right, so this is number 27 in the exercises, and it says, suppose a baseball is thrown vertically upward from the ground with an initial velocity of, and they just call it V naught, and that's feet per second. Its height above the ground after t seconds is given by the position function s of t is equal to negative 16t squared plus the initial velocity times t. Determine the initial velocity of the ball if it reaches a high point of 128 feet. So this is a pretty tough one, but I want everybody to go ahead, pause the video, give it a try, try to set some of it up, see what you can do, and then when you're ready to go through the solution, go ahead and unpause the video. All right, so we know that we're on ground level here. Let me use my pen here. I like to draw these out. So I'm standing here on ground level, and I am throwing this ball upwards with some initial velocity. So that's going to be some value in feet per second, although I don't know what it is. It's going to reach a maximum height of 128 feet. And then it's going to come back down. And And then once it gets up to this height here, it's going to come back down. So we're given this position function here. S of t is equal to negative 16t squared plus the initial velocity times the t there. So what I'm thinking here, and there's probably different ways to solve this, but remember, as it's going up, the velocity's kind of going down and down because it's going slower and slower until right at the top here we're going to get a velocity equal to 0. And that's really what I'm going to use in order to solve this, because after it reaches the top here and your speed becomes 0, then the speed's going to start increasing again as it falls back down towards the ground. So let's go ahead. We know that at 128 feet we're going to have a velocity equal to 0. So let's go ahead and find the velocity function here first. So that's just taking the derivative of the position function. So that's going to be v of t is going to be equal to negative, and using the power rule there, it's going to be negative 32t. And then remember that this v naught is just a value there, and it's t to the first power. So when we take the derivative, the t just drops off and leaves us that value. So we'll have plus v naught here. And we are looking for the time when the velocity is equal to 0. So what I'm going to do is I'm going to replace this v of t with 0, because that's the velocity that I'm caring about right now. So that's going to be equal to negative 32t plus the initial velocity. And then if I add 32t to both sides and then I divide by 32, I'm going to get t is equal to the initial velocity all over 32. So remember, at this point, I don't know what the initial velocity is, so I just have to keep it in here as kind of a constant variable, right? This is just some kind of constant here. So now I'm going to go back to my position function here, and I'm going to replace t with v naught over 32. So s of t is equal to, and really, what am I caring about here? I'm caring about when the height is 128. So I can actually go ahead and do that now. So I'm going to replace my s of t with the 128. And then this is going to be equal to negative 16 t squared. T is v naught over 32 plus the v naught times the t, which is v naught, that's just initial velocity, over 32. And really what I'm going to end up doing here is solving for v naught. So let me give myself a little bit more room here. So I've got 128 is equal to, this is going to be negative 16, oh, this should be a squared right there. I forgot, I left that squared out. Negative 16, and then v naught over 32 squared. I'm just going to write that as v naught squared over 32 squared plus, and v naught times v naught is v naught squared all over 32. I want to get a common denominator, so I'm going to multiply the top and the bottom by 32. That'll give me a 32 squared on the bottom and a 32 up here. And let me go ahead and do that with a different line here. So 128 is going to be equal to negative 16, and 32 is 16 v naught squared all over 32 squared. And let's go ahead and use the calculator to see what that reduces to. Alright, so we have 16 over 32 squared. So let's see if I do 32 squared and divide that by 16, I'm going to get a 64. So really 128 is just going to be equal to v naught squared over 64. Remember, I'm solving for my initial velocity now. Let me kind of go over here. So multiply both sides by 64. And right now I'm just going to leave it like this. 128 on the left times 64 is equal to V naught squared. I'm going to show you why I'm not going to multiply that out yet. Because now I'm going to take the square root of both sides to solve for my initial velocity here. And really, I'm going to write this as, I know 128 is 2 times 64, so I'm going to write this as 2 times 64 times 64. And that's going to be equal to V naught squared. And this is going to be, the square root of 64 times 64 is just 64. So I can pull a 64 out here. So this is 64 root 2 is going to be equal to, and I really should, I took the square root, so I shouldn't have that there, is equal to V naught. So my initial velocity is going to be 64 times root 2, and that will be feet per second. Feet per second. So that was a lot of work. It was a lot of work, and one thing that we're going to find is that we're going to be using the idea of it changing directions, and that's going to be where our velocity is equal to 0. So that's something that we're going to be using a lot when we do these types of problems. All right, let's go ahead and move on. Okay, so the last thing that we're going to look at from this section is average and marginal cost, and then we're going to define this term elasticity. And both of these are going to use derivatives. So here's the idea here. The cost function, C of x, gives the cost to produce the first x items in a manufacturing process. The average cost, which they denote with the C, with the little bar over the C here, is just the cost, that's the total cost, divided by the number of items that you produced, which makes sense. If you are making robots and your total cost is $1,000 and you built 10 robots, then your average cost per robot would just be $100, right? Because it would just be 1,000 divided by the number of robots that you made. And then the marginal cost, which is the derivative of the cost function, is going to give you the approximate cost to produce one additional item after you produced the X items, the independent variable. And then elasticity says if the demand for a product varies with the price according to the function D is equal to F of P, then the price elasticity of the demand is given by this function here. And we'll do an example with this function here. And remember that, well, don't remember. So the way that elasticity works is that if the quantity demand of the product changes drastically when its price increases or decreases, then we call it elastic. And if it doesn't change very much or at all, then we call it inelastic. Inelastic. And this is something that businesses and other manufacturers would use to determine whether or not they need to raise or lower their prices to see if it's elastic. All right, so let's go ahead and take a look at an example here. All right, so let's take a look at number 33 here. Drop my pen. This is in the back of the book, and it says, based on sales data over the past year, the owner of DVDs of a DVD store devises the demand function. D of P is equal to 40 minus 2P, where D of P is the number of DVDs that can be sold in one day at a price of P dollars. So the first one here says, according to the model, how many DVDs can be sold in a day at a price of 10? So that is pretty easy. All we have to do is just put in 10 for P, and we'll have 40 minus 2 times 10, which is 20, and that will give us a number of, the demand will be 20 DVDs. So with a price of $10, you just put it in the P there, and you'll get 40 minus 20, which is 10. The next one here says, according to the model, Let me put a little 20 DVDs. 20 DVDs. DVDs. All right. The second one here says, according to the model, what is the maximum price that can be charged above which no DVDs can be sold? So what they're asking at what price gets this demand down to 0. So we can just set up that function there. So that would be 40 minus 2p. P is equal to, that would give us a demand of 0. Nobody would want to buy them. And solving for p, we're going to end up getting p, excuse my writing, is equal to 20 bucks. So once you make a DVD that costs $20 or more, you're not going to have a demand for them anymore. So that would be $20 there. All right. Find the elasticity function for this demand function. Okay, so let's look up here, and here is the elasticity function there. So the elasticity function, E of P, is equal to, now this is the derivative of our demand function over the derivative of our price function times the price over the demand. Well, we know the demand there, so what I'm going to do is I'm going to pull the demand out. So we're going to take the derivative, and this is really just kind of rearranging this a little bit. The derivative with respect to price, that's what this means, the derivative with respect to price, and then pull the d out of our demand function, which is 40 minus 2p, which is 40 minus 2p, times the price all over our demand function, which is 40 minus 2p. All right, a little bit weird, but this is how we do it, and you can kind of separate it like this. So the derivative with respect to price of this function here is just going to be using the zeros out, and you just get -2. So this is going to be -2 times the p all over 40 minus 2p. And if we divide everything by -2, we'll get p over p minus 20. And so this is our elasticity function. For what prices is the demand elastic or inelastic? So remember, -1 is our kind of stopping point between being elastic and being inelastic there. So anything that is between -1 and really negative infinity is considered to be elastic, and anything between 0 and -1 is considered to be inelastic. So we mentioned here the elasticity function. We're going to set that equal to -1. So p over p minus 20 is going to be equal to -1. And multiply both sides by p minus 20, and you're going to get p is equal to 20 minus p. Solving for p, because we're going to add p to both sides, divide by 2, and you're going to get p is equal to 10. P is equal to 10. So this means that if p is between, the price is between 0 and 10, then our elasticity is going to be considered inelastic. And if the price is greater than 10, then it's going to be considered elastic. All right, guys. I hope that helps. If you have any questions, please let me know, and I hope you have a great rest of your week. Thanks.